Alright everyone, today we're diving into a paper titled, This Time is Different, an observability perspective on time series foundation models. So this research introduces a new foundation model for time series forecasting called TOTO. That's TOTO. It's a 151 million parameter model, specifically designed for, well, the unique challenges of multivariate observability time series data. They also present BOOM, a new large-scale benchmark to evaluate these kinds of models. So, we just mentioned that TOTO is a foundation model for multivariate observability time series data. Let's quickly break those terms down for a moment. A foundation model is essentially a large, general-purpose model that's been trained on a vast amount of data, which can then be adapted or fine-tuned for various specific tasks. And multivariate observability time series data, well, time series data simply means data points collected in sequence over time. Multivariate tells us it's tracking multiple different variables at once, and observability data typically comes from monitoring systems like servers or applications, giving us insights into their operational health and performance. Alright, and if you want to dive deeper into the practical side of this research, the authors have released the code for TOTO. That's their time series optimized transformer. So in their GitHub repository, you'll find the model implementation, pre-trained weights, and also code for evaluating it on benchmarks, including the BOOM benchmark they introduced. Okay, so it gives us a nice visual summary. Panel A shows TOTO is pre-trained on observability data, plus other public and synthetic datasets. Its architecture, featuring components like causal normalization and a student-team mixture model for output, enables zero-shot forecasts. Zero-shot forecasts essentially mean predictions on new data without specific prior training. Panel B uses what's called a principal component analysis projection, or PCA projection. This is a technique to simplify and visualize complex data, showing here the BOOM benchmark's unique statistical profile compared to others. And panels C and D highlight TOTO's strong performance, ranking very well on both BOOM and the GIFT-Eval benchmark. Okay, so gives us a more detailed schematic of the TOTO architecture we just broadly discussed. Panel A here shows the input multivariate time series first undergoing that causal patch-based instance normalization. Then it's transformed into patch embeddings, which means the series is broken into smaller segments or patches, and these are turned into representations the model can use. These embeddings are then passed through a transformer decoder stack, then unembedded and flattened, before finally going to the student-team mixture model for predictions. Panel B visually details this patch embedding process. And Panel C that shows the transformer stack itself, highlighting what the paper calls proportional factorized attention, with a specific 11:1 ratio of time-wise to variate-wise blocks, to handle both time and variable interactions. Okay, so gave us a detailed schematic of the TOTO architecture, now provides further context on TOTO's training and design choices. Panel A here really emphasizes the scale of TOTO's pre-training, showing its training corpus, which is the dataset it learns from, is significantly larger than other models, combining both observability and public data sources. Then, Panel B presents results from an ablation study. An ablation study is where specific components of the model are removed one by one to see how much they contribute to overall performance. The bars show the increase in negative log likelihood, which is a measure of prediction error, so a higher bar means that component was more important for good performance. We can see that removing the causal scaling, or the student-team mixture model, both key parts of TOTO's design, led to the largest drops in performance. So, after looking at TOTO's architecture and the importance of its components, now shifts focus to the BOOM benchmark itself, giving us a closer look at the data TOTO is evaluated on. Panel A here provides a breakdown of the domains covered in BOOM. We see a bar chart showing that application metrics make up the largest portion, around 41%, followed by infrastructure and database metrics. And Panel B offers some visual examples of these time series. For instance, you can see plots representing data like failed API requests for applications, CPU limits for infrastructure, and command executions for databases. This really helps visualize the kind of real-world observability data we're talking about. Alright, so after seeing what kind of data is in BOOM, digs deeper into its statistical characteristics, comparing it with the GIFT-Eval and LSF benchmarks. We're looking at distributions for 6 different statistical measures here. For instance, the KPSS statistic, that's KPSS, is generally higher for boom, shown by the pink line, indicating more non-stationarity. Non-stationarity means the data's statistical properties like its average and spread change over time, which really complicates forecasting. Boom also tends to show higher spectral entropy, suggesting more inherent complexity in the signals, and greater skew, meaning more frequent extreme values, highlighting its distinct and challenging nature. Okay, so after seeing those distributions and that highlighted boom's distinct statistical profile, now gives us some hard numbers comparing boom with other benchmarks like GIFT-Eval and LSF. This table details things like the number of series, the total data points, and importantly, the number of variates per series. Variates are just the different individual data streams or variables being tracked within each time series. For instance, boom has 350 million points, more than twice GIFT-Eval, and a median of 60 variates per series, which is way higher, indicating much more complex high cardinality data. Cardinality here just refers to that number of variates. This really quantifies the scale and multivariate nature of the boom benchmark. So we've seen boom's scale. Now shows TOTO's performance on another established benchmark, the long sequence forecasting, or LSF benchmark, in a zero-shot setting. This means models are tested without prior fine-tuning on this LSF data. We're looking at MAE, mean absolute error, and MSE, mean squared error, where lower scores are better for both. TOTO achieves the lowest MAE at 0.324 and the lowest MSE at 0.303. The best count row also indicates TOTO had the top score on 8 different metric comparisons, significantly outperforming others here. TOTO's strong performance on LSF, even in a zero-shot setting, really underscores the power of its observability-driven design. This research, I think it's a big step forward. It gives us boom, a much-needed challenging benchmark reflecting real-world data complexity, and TOTO, a foundation model that effectively tackles these challenges. This really pushes time series forecasting towards more practical, observable systems. That's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.